Hello, relativity friends. I got something fun here. I'm calling it a simple derivation of the geodesic equation. Okay. Now, when you use the simple in a sentence with general relativity, it's a relative word, a pun intended, because general relativity is rather complicated. And the normal way you derive the geodesic equation is something called the principle of least action, and then you use the Euler-Lagrange equation, and you do math. It's complicated. I think this is much easier to understand, and you basically get to the same answer. So I'm gonna go with this because this is the one I understand. Okay, and this is from the book General Relativity and Intuitive Introduction. The chapter in that book, General Relativity for Dummies. Since general relativity makes me feel like a dummy, I think this is appropriate. And I'll put a link in the description for this book. I like this book. I use it as reference all the time. Okay, we're going to start with the gradient of a scalar function. And it looks like this. So we got the del operator acting on this scalar field, the scalar function. Let's just call it a scalar. So we get the derivative of that with respect to the coordinates, right, times its basis vectors. It's obviously in Cartesian coordinates. All right, and we also have a vector, and let's say it's a velocity, the vector. It has its components, and it has its basis vectors. All right. Now we're going to multiply these together, which is going to give us a scalar, right? So we're going to have little v dot del f. Now remember, these are orthonormal basis vectors, so ex dot ex is 1, ex dot anything else is 0, and that applies to the rest of these. So we're just going to be left with 3 non-zero terms, and here's what we get. All right. Now let's do first I want to say this is telling us the rate of change of f, the scalar, in the direction of v. The rate of change of f in the direction of v. So it is a directional derivative in the direction of v, right? That's what it's telling us. Let's take an example. All right, here's a vector, and here is a scalar function. All right. Now let's dot these two things. Not yet. Let's take the gradient of this. So the derivative of this with respect to x is just 6, with respect to y is 6, with respect to z is 6. So this is the gradient of f. So it is the steepest rate of change of this function. That's what that means. Now let's dot it with f. All right, the same thing applies for the basis vectors. We just get 3 terms. So the negative 3 times 6 is negative 18. 0 times anything, 0. 3 times 6 is 18. So this is 0. Well, what's that mean? What's that telling us? It means that the scalar, the field f, this f, is constant in the direction of this velocity vector. This is constant in the direction of this velocity vector. So the takeaway from this is that v dot del f is equal to 0. This means that. Okay? Now let's switch to relativistic velocity, which is called u, and it's called the 4 velocity because it's a function of 4 coordinates, time and 3 spatial components. That's space-time. And we can write that using the summation notation as its components and basis vectors. Okay? Now, we want to make that equation we found up there a tensor equation. So one way to do that is just change this del operator to a covariant derivative. Now, warning, this works most of the time to change a variant equation to an invariant equation, just changing the del to covariant derivative, but it doesn't always work. I found that out the hard way. Okay, so we want to know the change in the 4 velocity with respect to itself. Okay, so we want to know the change in the 4 velocity. That's going to be the 4 velocity with respect to itself. Now, remember, one of the postulates of general relativity states that an observer does not experience any acceleration in free fall. All right, and you can look at it. You've seen these pictures many times. So a person on Earth in a uniform gravitational field of 1g would The physics would behave exactly like it would if there's a person in a rocket ship that was accelerating at 1 g. These people experience the same feeling. Okay. So this means that the geodesic in general relativity is defined as a path in spacetime that follows the curvature of spacetime itself. No external forces are present. So uh, someone didn't push you or shoot you out of a rocket ship or anything. This means that the change in the forward velocity is zero along the geodesic. So if we're traveling along a geodesic in spacetime, our forward velocity vector is zero. All right, so that makes the definition of geodesic then the directional covariant derivative, that's what we've been talking about, of the forward velocity in the direction of the forward velocity is zero. So we take that gradient equation we saw above and we change it to this. So these are the components of the forward velocity times the covariant derivative of the components of the forward velocity, right? So this is the covariant derivative of u mu with respect to the coordinate alpha times the component u alpha. That's what that means. All right. Now, we know how to take the covariant derivative at this point. We've done it many times. Okay. So when you take the covariant derivative of something, and we got a one index tensor here in the contravariant position, first thing we write down is the partial derivative of that with respect to the coordinate, which is x alpha. And since this is in the contravariant position, we had a plus sign, remember? Then we put our Christoffel, the symbol here, gamma. Now look over here. There's only one free index in this whole equation. It's that one. This is a summation index. So we have to put that there. All right. So then we put our alpha here, and we put the component here, but we need, in order to make this a tensor equation, this needs to be a summation index. So we make up a new one. We make up beta. Now we distribute this inside and we get this equation. Okay? So far, so good. Now, we can write this here as the change in the coordinate x alpha with respect to tau, which is called proper time. Now, what is proper time, you may ask yourself? Let's think back to special relativity, okay, where we saw an equation that looked like this. We had time times this Lorentz, the factor it's called the gamma, the factor, is equal to tau. So this time is the time of someone at rest, and this is the time of someone moving. So proper time means that if you're in motion, you have a clock with you. This is your time in motion, and this is the time of an observer who's at rest, right? So if I'm at rest and you're traveling at 90% the speed of light, I measure 24 hours go by, and you measure, according to this equation, this. So I put in 90% the c, I square it, the c's cancel, 1 minus 0.81 times 24, about 10 and a half hours. So you say, no, it's only 10 and a half hours to go by. And I say, no, it's not. It's 24 hours have gone by. So a moving clock runs slower than a clock at rest, right? So that's proper time. All right. So now where were we? Oh, we had this. And we said we're going to define this mu alpha as the derivative because that's velocity, right? So the change in distance with respect to time. So it's the same equation. It's just relativistic. With respect to the proper time, we're going to put that right there. Okay? So that makes this equation look like this. Now look here. These two things are the same. So we can get rid of these. And I hope no mathematicians are watching. So we get this equation. The change in the forward velocity u mu component with respect to the proper time tau. Okay? Now, since we're going to set this equal to 0, then this is equal to 0, right? Now, since mu is equal to the change in the x mu coordinate with respect to tau, we can just put that in for right here, right? So we're going to put this in right there, and we get the partial of this partial with respect to tau gives us the second derivative of x mu with respect to tau squared. We put that back in like this, and this is actually the equation of a geodesic. Now, this might not be the form you're used to seeing it in. Here might be the way you're used to seeing it, because what is mu alpha? That is the change in x alpha with respect to tau. What is mu beta? The change in x beta with respect to tau. This is probably the form you're used to seeing it in. Anyway, I thought that was so much easier than the normal way to do it. All right, see you later.